This episode of Science Max is all about building things strong. 2.
And let's do 3.
An arched bridge, giant house of cards, magical stacking books, and more.
Oh, I thought they were gonna do it.
All on this episode of Science Max Experiments at Large.
Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape. And so it fits in just like that, and you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take up the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge, so you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide, and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arched bridge so strong. And that's what we're gonna do today. We're gonna max out an arched bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Center. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hey, Phil, how's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay, what's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do, oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I...
Where have you been? Breathe.
The remote ran out of battery, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the sugar cube bridge, you had a chance to look at it, right? This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So I'm going to start the bridge here, and I've already created a thing that we can use to put the sugar cubes on as we go up, so that we can make sure that it becomes a perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Wow.
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay.
Yep.
To stay right
on.
there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
Oops. An egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh? My weight can be supported by just 8 eggs. Science! Whoa, careful.
Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive.
A massive sugar cube bridge,
Yep.
right? High fives for that.
The moment of truth comes when we take out the support and...
Yeah! It works!
Awesome.
Okay.
Very nice.
Giant sugar cube bridge. So do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base. So
that's what it's for, right? We can put weight on there?
we can definitely put some weight.
One to start?
Let's start off with one.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah! 1 book! Yeah! All right. Sugar cube bridge,
1 book.
2 books.
Are you nervous?
Yeah! Sugar
books.
sugar cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the 3rd.
So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube
Yeah,
works.
you're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely, I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop.
It's a piece of glass that has a long snaky tail and a bulb at one end. So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water. What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge. Until you get to the tail. Just the tiniest break in the tail, and it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries. But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant. Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Overwhelmo.
You again.
I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very posterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates.
There we go. I've made some abutments out of giant crates, and this is where we're gonna start our bridge, and they start there, and it goes in a big arch, but we're gonna be using
I brought milk crates!
milk crates! High fives, high fives.
So we start our bridge,
This is a straight line, it's not an arch.
It's not an arch.
but it's clear we have a problem.
Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. This is like 2 straight
We
lines.
have 2 straight lines,
It's
yep.
like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a big
a
one
gap
here.
there.
It's
Well, I
not
mean-
making our bridge very solid.
There's only one way to find out for sure,
You can try it.
is to pull this out and see if it stands up.
Let's do it.
Okay. So, didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube,
Milk crates are cubes.
but we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes.
So they were tall, wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could cut
That's
it.
gonna take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right? We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid.
Good.
And it works. But
It's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiments and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and we'll
it.
make it one secure structure.
Ah, instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay, let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with.
This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up.
keep on building by making triangles and putting another card across the top like a roof.
Then, when you're ready, you can start to make a second layer.
It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it.
There we go. Ha-ha, a house of cards. Now, let's max it out. Shh, backing away slowly. Backing away slowly.
To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall.
Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again.
Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates. Once we get the wedges in, the milk crates have support at their tops and they make a perfect arch.
Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it.
We pull out the support and
It stands!
it works! The bridge supports itself! Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat and
We built a second arch
We sure did.
so that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Sonia puts on a helmet and gives it a try. And sure enough, it works!
Yeah! Milk crate bridge!
Milk crate bridge!
Milk crate bridge! Milk crate bridge! Milk crate bridge! Woo-hoo-hoo-hoo! Science Max experiments at large. Milk crate bridge!
Yay for science!
High five! High five!
Science Max!
We're flying again on Science Max.
Gliding squirrel.
Throwing things, spinning things, tumbling things, and maxing things out just a little too much.
Go, go, go! Go, go! Wait!
Keeping things up in the air is what's on the runway for this episode of Science Max Experiments at Large.
Well, hello there, Science Maximites. Today we're going to be flying on Science Max Experiments at Large. Take a look at this. It's my paper airplane. Give her a bit of a throw and she flies amazing. Now take a look at this. This one is lighter than air. It's a helium balloon, and guess what? It flies on its own. See you later. Well, just hold on a second there, friend. What's this whatchamacallit called? I'll tell you. It's called a hoop glider. Give it a toss and she flies really well. But today we're flying in a whole new way, Science Maximites. I know it sounds like we've covered all the bases for flying, but we haven't. Come on, follow me. Oh, didn't actually realize how much these goggles would fog up. Where was I? Oh, right, we're flying today on Science Max. Come on. Today, we're going to be building a tumble wing. That's a kind of paper airplane that flies on a cushion of air. This is a big mouth tumble wing. It doesn't look like much because, well, it's not. It's just 2 strips of paper taped at either end. But what you do is you throw it in the air and you walk along behind it with a hard surface like this, and that little scoop of air keeps it flying. And here's how you can make a tumble wing of your own. But first, a word about paper. Did you know that paper comes in different weights? The kind of paper you get from the printer is actually pretty heavy. The ideal paper to use for tumble wing making is from a phone book. You may not have a phone book at home. They're kind of rare right now, but its paper is very, very thin and the perfect for tumble wing flying. Now, if you don't have a phone book around, you can use newspaper. It works almost as well. What you do is you cut out some strips of paper, and you just need 2, and you put them on top of each other, and then you offset them, which means you take the top one and you slide it over till there's about maybe a centimeter, 2 centimeters, something like that. And then you take your handy dandy science tape, which is the same as regular tape, except you use this tape only for science, and you tape the edges very carefully like that, and flip it over to the other side. Make a little tape on this side, just like that, and there you go. You have a big mouth tumble wing. Now you also want to tweak it just like you do with a paper airplane. You want to curl the paper a little bit, curl this side a little bit, and let's see how it flies. You'll know you have it right when it doesn't go to the left or right, but just opens up and tumbles straight down. Ah, not too bad. That one curved a little bit, so I'll have to tweak it a little more. Now, the other thing you're gonna need is a nice hard surface. The kind of signs that you get when there's an election are perfect. I happen to have a few of these sitting around, and they are made of something called corrugated plastic. They're very light, but they're also very hard. So you can use this, but you can also use cardboard if you don't have any of these around. So what you wanna do is get your tumble wing and your hard surface and flip it in the air, get it flying very nicely, and then walk behind it with your board, and a scoop of air will be behind it, and it will fly. But it may look easy when I do it, but that's because I've been practicing quite a bit. So here are some tips for tumble wing flying.
Tumble wing flying tips. When flying your tumble wing, you want to be indoors, away from any wind or other kinds of moving air. A long hallway or a big room is best so you don't run out of space. The angle you hold your board is important. Too much tilt or too little, and it won't work. Keeping your tumblewing in the air is mostly about the speed that you walk. Too fast and the tumblewing will go over the top. Too slow and it'll fall. Finally, practice, practice, practice. Happy tumblewing flying!
Now I just need an expert to help me. Okay, let's see here. Lisa from Logic's Academy. She'd be perfect. Okay. There. And, oh wait, I need a lab coat. Oh, and Lisa needs a lab coat. There we go, Lisa's lab coat. Good, my lab coat. All right, my turn. Oh, my lab coat changed color again. I'll fix it later. Lisa's gonna be here any minute.
Oh,
Hey!
that was so fun!
Oh, did you like the portal?
I loved it. Hi, Phil.
Lisa from Logic's Academy, I'm glad you're here. Your lab coat changed color as well, though. It's supposed to be yellow. I think we had a glitch.
I kind of like it though, blue.
No, but we gotta do yellow. Yellow is the Science Max lab coat color.
Okay.
So, we are here to talk about the tumblewing. I've got my big mouth tumblewing here.
I have
Got
mine
yours?
too, yeah.
Now, what are we wanna max it out, obviously. What else can we do?
Well, actually, there's a lot of different designs that we could try. This is a big mouth tumblewing. There's also tumblewings that are just a straight sort of single wing.
Oh.
And then there's some that are like an actual airplane or a glider.
Ooh, and we can max them all out.
Of course.
All right, let's get started.
Let's do it.
And we'll get the yellow lab coats.
And I really like the blue.
We gotta get the yellow. There, now we've got our yellow lab coats. I've got my big mouth tumblewing, and I got my board to push the air.
Oh, look at that! I voted for you.
You did?
I did.
Oh, you were the one. Okay, so let's talk about the science going on behind this air surfer.
Okay, so just like in an ocean, if you were surfing in an ocean, you'd be surfing on a wave of water. Right now, our tumblewing is surfing on a wave of air that you're creating with a board. And air and water are actually both fluids.
Oh, cool. So we
They
can.
behave the same way.
So it really is surfing.
It is surfing. And actually, sometimes we call those air surfers.
Cool. Well, why don't we have a surfing competition? Because I actually have here a Team Phil board and a Team Lisa board. Okay, so what do you want to have a race?
Yeah, absolutely.
Okay, you want to take this one? This one flies really well.
Definitely.
I'll make a new one.
Okay.
Welcome to the Air Surfing World Finals, almost live from Science Max headquarters. I'm Jim and I'm joined by Chuck. Today it's Team Phil versus Team Lisa.
Team Lisa has a lot of heart, Jim.
But Team Phil is on his home turf. Let's see how they do. Round one is, of course, the tumblewing race.
And a great day for air surfing. The teams are ready, and there they go.
Ooh, Team Lisa looks like she had some trouble starting. Team Phil has already pulled ahead, but Team Lisa is off the marks now.
I think that beginning fumble might have cost her.
Let's see. Team Phil with a commanding lead, but Team Lisa's catching up. Oh, Team Phil loses his tumblewing at the last minute. A great dodge and a pass by Team Lisa. Can she hold it? And no!
Taking 10 steps back is the rule when you drop your tumblewing, Jim. It's anybody's game.
Looks like Team Lisa fumbles her start. Phil pulls ahead. Can he be caught?
Almost at the finish.
Yes. Team Phil with the win. What an upset.
All right, you had a lot of practice with that one.
Yeah, okay, so you got another design?
Yeah, let's try the single wing
New
one.
design.
Okay.
So at the end of the first round, we have Team Phil with 1 point, Team Lisa with 0.
But now we go to the second round where the design changes. We're now looking at a single wing design. It still tumbles like the big mouth tumblewing, but made from a single wing.
Does that make them harder or easier to fly, Chuck?
A bit harder. They're faster and more maneuverable.
If you wanted to, you could research tumblewing and you would be able to find this design. And this is what these show you where to fold it.
Yes. So the dotted lines or the dashed lines are where you would fold, and the solid lines is where you would cut.
What's more, Team Lisa has more practice with this version.
And they're off. Oh, Team Phil with another early lead, but Team Lisa's catching up.
Phil doesn't have much practice with this version, and it's starting to show.
You're right, Phil fumbles. Oh, Phil fumbles, and Lisa passes him for the win. There we go. At the break, we're all tied up with Team Phil and Team Lisa with 1 point each.
Look how well mine's going. This is an ornithopter. It's a machine that flies by flapping its wings. When people were still trying to figure out how to get something to fly, they thought, copy a bird. A bird flaps its wings and it flies, just like this. So, why don't we have airplanes that fly by flapping their wings? It turns out that flapping wings is actually complicated mechanically. First of all, you have to tilt the wing when you go up so it doesn't take as much air, and then turn it so you push more air on the downstroke. So flying like this would be kind of hard for an airplane and really hard to do on a large scale. So humans came up with this. Our propeller. Our propeller catches the air, and if you spin it fast enough, it gives you lift. So if you orient it upwards like a helicopter, it will give you lift, or if you orient it this way, it will give you thrust, just like an airplane. So that begs the question, why don't birds and insects use propellers to fly? Turns out, though, that rotating a propeller is really hard to do with something that has muscles and tendons. So in the end, birds fly by flapping their wings, and humans first learned to fly by rotating a propeller. Science. Lisa and I are air surfing. We've tried 2 different versions of tumble wings, but now Lisa has a new design, one that doesn't spin as it flies. Okay, so what do you have now?
Oh, check this out, Phil. This is a mosquito glider.
All right, so it's like a paper airplane.
Yeah, but it's not made of paper. It's made of a light foam.
Ooh. The mosquito gliders work the same way as the tumble wings, but because they're much larger, they're much harder to control. I got it. Oh, no, 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 no. Oh! Almost into the stuff. Not bad, though, right?
You got it.
This is very tiring.
This is really hard. It takes a lot of flying time to master.
We got the hang of it, but we quickly learned that you have to run a lot faster with the gliders. And we were soon out of breath.
Whoa, sorry. You gotta be in good shape for this.
Turns out a bigger glider is much harder to fly. So,
Ultra maxed out mosquito glider.
we made it even bigger. Why? Well, because it's Science Max.
Bigger board.
We needed a much larger board and tried first with 2 people.
Ready? Going.
And then with 1. And the most we were able to get it to fly was not a lot. Our conclusion?
Large airplanes just don't fly very well.
Well, homemade ones.
But we can try something else.
Okay,
Let's try something else.
let's try something else.
Today only, I got a super special on anything that can fly. Go on, pick something out. Oh, you had the paper airplane. Oh, good choice. Good choice. But guess what? Paper airplanes don't fly. Full price. Yeah, I know, but before you start arguing with me, you need to know the difference between flying and gliding. A paper airplane does not fly, it glides. You need constant thrust in order to fly. If you do not have constant thrust, then you glide. Take this bird. This bird can fly because it flaps its wings. It has constant thrust. On sale. But this airplane cannot fly. You give it some initial thrust when you throw it, but after that, it can only glide. Full price. But look at this. It's an airplane powered by a propeller on an elastic. Now we're talking constant thrust. It can fly. On sale. But it can get confusing. I mean, look at this flying fish. Nope. Flying fish cannot fly. They can only glide. Full price. Look at this. It's a cute little flying squirrel. He climbs a tree, jumps off from a high branch, opens his legs, and there's a little flap of skin there that allows him to sail to another tree. Haha, flying squirrel. No, not flying, no constant thrust. Gliding squirrel. Full price. Okay, tell you what, you came all the way down here, I'll make you a deal. Check this out. Flying fish, now it has a propeller, it has constant thrust, it flies for real. And ditto, squirrel with a jet engine, And now you know the difference. Something that flies has to have constant thrust, otherwise you're just gliding. Squirrel away! I forgot to gas him up.
look at those clouds. Aren't they nice? Did you know there are different names for clouds? Like those clouds right there? Those are cumulus clouds. They're the kinds that look like cotton balls, really fluffy and light. Well, they're not exactly fluffy and light. First of all, they're not fluffy, they're wet. It would be sort of like being a very dense fog, and it'd be very wet if you were in that cloud. And they're also not light. In fact, they're not light at all. That cloud right there weighs about 500,000 kilograms. That's the same as 100 elephants. 100 elephants just floating around in the sky? Come on, how does it do that? It does that because it's so spread out. But water is very heavy. Interesting to think about. 100 elephants just floating around in the sky above our heads at all times. Almost makes you want to go inside.
Our air surfing tumblewings worked well, but our mosquito gliders were a bit too maxed out to fly really well.
Large airplanes just don't fly very well.
Well, homemade ones.
But maybe we should try maxing out the tumblewing just to see what happens. So we did!
Okay, Lisa, I'm gonna throw it, and then you're gonna push the sign.
What?
Go!
Ah!
Wait.
Oh, did it go? What happened?
It didn't. Whoa! It didn't work.
We tried it, and and it turns out, yeah, it doesn't fly.
Go! 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 Wait!
Ah!
But I mean, this is science, Max, so of course we had to at least try maxing it out.
Phil,
I don't know if this is working.
it's heavy.
It's very heavy. Okay, maybe we should go back to a slightly smaller version.
Sounds like a plan.
Okay.
High five?
High five. This is a boomerang. Boomerangs are from Australia, and the cool thing about boomerangs is when you throw them, they come back. With practice. That was close. When you throw them, they come back. And it comes back. It comes back. Come back. Come back. So, why does it come back?
Well, if you take a look, it's made of two wings, like airplane wings, but with one important difference. You see, a wing has a shape called an airfoil, and this gives lift. But check it out. The boomerang has one airfoil pointed this way and the other pointed the other way, which means if you spin it in the right direction, each wing will get lift as it rotates. But how does lift make it come back? Well, that's the trick. You see, you throw it sideways. The lift from the wings makes it go in a big circle and come back to you.
So when you throw a boomerang, this side starts to go this way and it gets a little bit of lift. Then this side gets a little bit more lift, and then this side gets lift, and each time it gets lift, it starts to turn just slightly. So as the boomerang spins, it describes a nice big arc in the sky and comes right back to you. Ha-ha! And that's how a boomerang works. Thanks, Phil. No problem, Phil. Hey, do you want to get lunch? Yeah, lunch sounds good. Okay, come on. Well, the Science Mech headquarters has a nice cafeteria.
We've tried air surfers of all shapes and sizes. And what have we learned?
Maxing out an air surfer by making it bigger is really difficult.
Very difficult, yeah.
So what we've decided to do is go back to our original big mouth tumblewing and instead do it on a maxed out obstacle course!
Tumblewing surfing round 3, the maxed out obstacle course. Let's take a look at the obstacles. The tree slalom, the podium ramp, the hanging hoop, ring walk, wall of boxes, ladder tunnel, side hoop, ball promenade, and the barrel run.
So here's how we play. I go through and then you follow me. And if you make it through an obstacle and your tumblewing's still in the air, you get a point. And at the end, we count how many points we have and we see who won.
And it looks like they're ready to start. Here we go!
Where are you, Team Lisa? Oh. Whoa, yeah. Oh, no. Okay, what do I do with the boxes? What do I do with the boxes? Going through the boxes! Definitely didn't make that one. Recover! Ah! Oh. Okay, definitely lost a point there.
I'm almost there! Right behind you!
Yeah! Uh-oh! Knock the barrels over, getting
I
through
get
the
an
finish
extra
line.
point for
And Team Lisa! Oh, yeah! Nicely done, high five.
Awesome.
See how the airflow from the board keeps the air surfer in the air? Well, the trick is to give it just the right amount of air to keep it in control. Not too fast and not too slow. That's the science to good tumblewing flying. So, with the points from the last round added up, Team Phil and Team Lisa are tied again.
You know what that means? Tiebreaker! Thanks very much for watching Science Max Experiments at Large Tumblewings. You want to go first?
I do. Let's do it.
Okay, you go first this time, and then I'll follow you. I think it's easier to go first. So, okay, ready?
Yeah.
You ready? Set, go.
Science Max!
Science!
Today's Science Max is all about balance.
Okay.
If it's a potato or if it's me, figuring out how things balance is what we're all about.
It works really well!
Swinging, spinning, and staying put. Today on Science Max Experiments at Large.
Greetings, Science Maximites. Today, we're going to be talking about balance, or what you call balance in science, which is center of gravity. Now, the center of gravity is a place you can find in any object where it's equally balanced on all sides. I balanced this spoon on the eraser of this pencil, and where the spoon is balancing is its center of gravity. But if I take this little tiny dime and put it in the spoon, it doesn't balance anymore. But if I put the dime in this spoon and balance it in a different spot, I can find the new center of gravity, and the spoon balances again. Here's another experiment you can do. Take a potato and a ruler or a stick. Try to balance the potato on the ruler. I'm gonna save us both a lot of time. It's really hard to do. The potato does have a center of gravity, but because of its shape, it's going to be really hard to find and really hard to balance. But if you take some forks and you stick them into the potato, you're no longer just trying to balance the potato, you have to balance the forks and the potato. And it gives it a very different center of gravity, which makes it a little bit easier to find and a little bit easier to balance. Ha-ha!
Whoa! Let's take a closer look at how the center of gravity works. Using our potato. No, that's too close. Back off a little bit. Okay, good. If you want to find where the center of gravity is, you can hang an object and draw a line straight down. Then hang it from a different spot and draw another line. Do this 1 or 2 more times and you can see where the lines meet is the center of gravity. If our potato was balanced on a stick, the center of gravity is a long way from the stick, so it's going to be pretty hard to balance. Now, let's stick some forks in the potato and try again. One line there, a line there, and a line there, and you can see that the lines all come together down here. That's right, the center of gravity doesn't have to be on the object. With the center of gravity way down there, when we try to balance the potato and the forks on the stick, you can see the center of gravity is much closer to the stick. That makes it way easier to balance.
Now, because you're Science Maximites, I'm sure you know that a potato and forks is just the beginning. Everything you have in your house has a center of gravity, which means, theoretically, you can balance anything. Try it yourself. Find things around the house and see if you can get them to balance. And if you can't, try adding things to increase the center of gravity and make it a little bit easier. Now we're gonna max it out. That's why I'm gonna go to the Center for Skills Development and Training, and we're gonna explore center of gravity even more. See if we can get something to balance. And what better thing to balance than me? Oh, Right. Hey, this is Sandhya and Swapna. No, Sandhya and Swapna.
Right.
And they are going for their PhDs in science. And you guys, thank you for coming.
Thank you.
Work with Let's Talk Science, right?
That's right.
All about science education, just like us. And I'm glad you guys are here because I need to max out this. Oh, look at it balance. Whoa. Hey, whoa. Okay, I got it. It's fine.
Good. So we're gonna get a gigantic potato?
No, I thought we would use me instead.
So you're the potato.
Yeah, I guess I'm the potato. All right. And I need something to balance on.
Well, how about a tightrope?
Oh, yeah, a tightrope. Have either of you done a tightrope before?
Nope.
Me neither. All right, let's set one up.
All right.
Okay, good. Yeah, I guess it's great.
We're gonna take our balancing potato experiment and max it out. To get a potato to balance is pretty hard, but if you stick forks in the potato, it works a lot better. In our maxed out version, we're gonna balance on a slack line, which is sort of like a tightrope. It's a flat strap tightened between 2 points. And in this version, I'm the potato. And instead of sticking giant forks in me, which is not something I want to try, Sandhya, Swapna, and I are going to experiment to see what I can do to improve my balance.
There. We're using this ratchet strap above a crash mat because we only have it about 3 feet off the ground, but it's still going to be really hard to balance on, right?
Right.
Okay, so who gets to go first? Okay, here we go. Ready? Hey.
Got it?
No. Okay.
I think what you need to do is spread your mass out more to be able to find that center of gravity easier.
So I should balance on one leg?
Start by trying to put your arms out.
Let's try this again. Trying it again. All right.
All right, arms out.
Okay.
Let's see if this works.
Okay, so when I say, you're gonna let go. Ready?
All right.
1, 2, 3, go. No!
It's a little bit better.
It was a little bit better.
A little longer.
That way I went from 1 second to 3 seconds. Yeah!
Yes.
I would like to actually take 1 step.
Okay.
That would be nice.
Well,
What else can we do?
maybe we can try weights. Try and hold them out.
If I have weights in my hands, that would increase the center of gravity in terms of putting
it
the
out.
weight on the outside. You guys have something we can use?
Sure, yeah.
Okay, good. Wow, these are heavy. Okay.
These are weights.
Yes, they are. Well, that's what they're for. They're supposed to be heavy. Good call. When I hold this one, and I'll borrow your shoulder, Swapna, and then when I say, Sandhya, pass me the other weight. Here we go. Ready? And pass me the weight. No. Okay, that didn't work. Okay, good. Whoa. Okay, let go. Okay, let go. Oh, no. Oh, it's really hard. I feel I would work better if I could lift the weights up, but they're too heavy for that.
All right.
So, what else can we do?
Well, tightrope walkers use a long pole so that they can balance on a tightrope.
That's right, I've seen that. Do we have a pole?
I think go find one.
Okay, great. I'll put the weights away. Have you ever heard someone say, I will be back in a jiffy? Well, now you can tell them that's almost impossible. You see, a jiffy is an actual measure of time. It's 1/100th of a second. You see this timer? The first number is seconds. The second number is tenths of a second. And that third number that you can't even read, it's going so fast, that's hundredths of a second. Each one of those is a jiffy. Here are some things that happen in a jiffy. A cheetah moving top speed travels 20 centimeters. A hummingbird flaps its wings almost once. Can you blink in a jiffy? Nope, takes 10 jiffies for that. How about snapping your fingers? 8 jiffies. So the next time someone tells you, I'll be back in a jiffy, you can tell them it took 170 jiffies just to say that.
So I tried walking the slack line, and I wasn't very good at it. Holding my arms out at my sides seemed to help a little. Then I tried holding some weights to see if that would make any difference, and the weights were so heavy, I couldn't really hold them out very far. Now the plan is to try a long pole. Tightrope walkers use long poles to help them balance. The longer the pole is, the more it affects your center of gravity, especially because you can move it up and down to help you stay balanced.
Ta-da!
Nice. So the important thing on this is what? The balance, right?
Yeah, you
That's
want to
right.
find the center of gravity of that as well.
So
you
try
can
and find the center of the
balance
pole.
it.
The center is right there. That's where it balances.
There, you got it.
Okay. How do I hold this and get up on the strap?
I'll help
You're
you.
gonna help me? Okay. Oh, okay. Uh-huh. Whoa. Whoa.
You good?
Okay. I think I got it.
Okay.
Yeah. Whoa.
You're balancing.
Check it out. Hey, this isn't so bad.
Hey, look at that.
You can really use it to help correct when you start to fall. You just move the pole, and that's totally helping my center of gravity stay right in the center above the strap. Whoa. Whoa.
You can do it.
A long pole can help tightrope walkers and me balance in two ways. First, it lowers my center of gravity. Normally, a person's center of gravity is about here, but with a pole, it changes to way down here, much lower to the thing I'm walking on. But a long pole also helps in another way, because in order to fall off the rope, I have to rotate. It's easier to rotate something that has mass in the middle than it is when the mass is spread out. That's why you put your arms out when you want to balance. A pole works just like your arms. The mass gets spread out way more, and it makes it much harder to rotate around the rope and fall off.
There you go. Center of gravity. We're done. Usually we don't have it figured out this quickly. Usually we struggle a little bit more. All right, high fives.
Way
we did
to
it.
go.
Way
Awesome.
to go. So we did it.
Yeah.
We achieved what we set out to do, balanced with a pole. So how else can we use science to make my balance better?
Well, tops are great because when they're spinning, they balance.
That's right. So the forces used when something spins is something I can use.
Yeah.
All right, this calls for another small experiment. Are you guys good here?
Yeah, sure. We'll keep practicing.
Awesome. All right, back to the lab.
Bye, Phil.
Here's another experiment that's all about balance. Take a pencil and try to balance it on its tip. Doesn't work that well, does it? But if you take a pencil and stick it through a circle of cardboard and try it again, it works. The reason is because this circle is spinning, it creates a force that keeps the pencil standing up. As long as the circle is spinning fast enough, it counteracts the force of gravity because of the conservation of angular momentum. The conservation of angular momentum. The conservation of angular momentum.
Science Max presents Ways to Sound Super Smart. A top will balance when it's spinning. It works because it spins. But why say it that way when you can impress your friends and all the adults you know by saying conservation of angular momentum? Why does a top spin? Because of the conservation of angular momentum. Between you and me, we know that it boils down to the fact that it's spinning. But conservation of angular momentum is how you say it if you're studying physics in university. Just remember to thank Science Max when you impress everyone by telling them a top balances because of, say it with me, the conservation of angular momentum.
Now, let's max this out. Gyroscopic force is pretty amazing. Because this bike tire is spinning, it's hard for me to move it. But it's really hard to see how much it resists a change in orientation unless I do this. Ha ha ha! It looks like it's defying gravity, but really it's because the amount of force needed to change its orientation is more than the force of gravity pulling down on it. It won't last forever, only as long as the bike tire keeps spinning. But you gotta admit, it's pretty cool science. Whoa. Whoa. Science. Look at that, it totally balances.
Yeah.
So this is a great way to balance. Do you think it'll work if I hold it?
Well, let's see you try.
All right.
right.
So I'm gonna use you to get up on the thing, and Cindy, you go give her. Yeah, that's good. And spinning it up. Here we go.
Ready?
Yep.
Okay.
Yeah. Whoa. You can feel it. I can really feel it resisting, and
Yeah.
I think it would work.
I think it just needs to be spinning a lot faster.
That would make even stronger, yeah. It kind of hit my chest, so.
You know what? Maybe you should keep it out to one side.
Well, it's still spinning, yeah.
Well, that.
I think you need two.
Oh yeah, you're right, one on either side. It'd be great if we could actually have some way I can keep my arms free though.
Yeah.
Oh, I know. Get two wheels and we rope them into some sort of backpack situation.
What?
And we have a way for you guys to get the wheels spinning really fast.
I don't know.
No, I have it all in my head. Trust me, come on, I'll show you. I'll show you. Wait, you guys go around. Come, don't go on that side of the. Time for a mini-max. Here's how you can use the forces of things spinning around to defy gravity. Well, sort of. Take a ping pong ball and put it in a plastic container like a cup, or this is the top of a CD spindle. Put it in and start spinning it around. If you do it right, you can get the ball spinning only on the sides of your container and not touching the bottom. That's centripetal force at work. Oh. It works a lot better and is much more impressive if you have something that doesn't have a bottom. Fortunately, I do. This bucket doesn't have a bottom. Put the ping pong ball in the bucket and spin it around, and if I'm very careful, I can lift the bucket into the air and ta-da! I'm defying the force of gravity. Science! Now I know what you're thinking. You're thinking, Phil, is that it? Is that all you're gonna do? No, of course not. This is Science Max Experiments at Large. This is a garbage can with no bottom in it. And this is a bag of golf balls. Let's see what happens when we put them together. Well, I managed to keep one golf ball in my garbage can. But as you can see, it works really well. And there you go, sort of maxed out. This is a garbage can with the bottom cut out, and this is a soccer ball. I'm gonna see if I can keep the soccer ball inside the garbage can using centripetal force. Okay. It's working! It's very tiring though. How do you throw out a garbage can that's been used? Science! Here's a fun experiment you can do that plays with the forces created when you spin something. Get a flat platform or a tray and tie rope to every corner. Get an adult to help you with this. Then you get a cup of water. Use a plastic cup, definitely, just in case. You put it on the tray and you start spinning. Now the force is created when you spin something. Centripetal force pulls the water to the outside of the circle. And because the centripetal force is stronger than the force of gravity, no water spills out of the cup, even when it's upside down. You slow it down very carefully, you'll see that all the water is still in your cup. Now, I definitely suggest you do this experiment outside, and I definitely suggest you do it with an adult. Because when you get tired, which you will, if you don't stop it carefully, you'll have to explain what you've been doing. Science!
Using science to improve my balance has totally worked so far. So now, Sandia, Swapna, and I are trying to figure out how to use the forces created when a wheel spins to help me balance. We need a spinning wheel on one side and one on the other. I've decided to take two bikes and remove the handlebars, seats, and front wheels, then cross them over each other and attach them to a backpack. Sandy and Swapna can use the pedals to spin the tires fast, and I will use the gyroscopic force to balance. Or at least, that's the plan.
Behold, the Gyroscopic Stabilization Backpack! Stabilization away!
I'm excited. Okay, you think it's gonna work?
I think so. I'm kind of skeptical.
Really? You're skeptical? Why?
I don't know. I don't know if you can do it.
I don't know if I can do it either, but that's why we do science!
Let's see it.
Okay, spin me up. Okay. Oh,
Ready?
yeah.
All right.
And, oh, ready? Go.
Yep.
Oh, yeah. It's working.
Cool.
It's working.
It's actually working.
It's good. Oh, what's getting harder? It's getting harder.
Uh-oh.
Oh, that worked really well until the wheels stopped spinning.
Yeah.
And then what happened?
Well, when the wheel was spinning, it was resisting motion in all directions so that you wouldn't fall.
Yeah, but when they stopped spinning,
You didn't have that anymore.
that doesn't do anything. It's just a 50-pound weight on my back.
Yeah.
Exactly.
Right. So I guess that's why tightrope walkers don't use spinning wheels. They use a pole instead.
Right.
But we've proven that they can.
Exactly.
Yeah. Max out, high five.
Yeah.
Woohoo! Yeah!
I now have the balance of a ninja circus performer thanks to...
Science!
Thanks for watching Science Max Experiments at Large. Okay, spin me up. Spin me up. And we'll do some more science. Gyroscopic backpack to the rescue. All right, let's go.
Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet. You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction. And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together. Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch. And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off.
So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Centre. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh,
we'll
via the portal?
Yeah, by the portal.
Oh, okay.
You sure?
I
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay,
No,
don't worry about it.
No,
No,
I think
it's
definitely.
fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You could also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery.
Yes.
More voltage and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was, okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, Do not use a drill unless you have an adult to help you out because drills can be very dangerous. This one goes at a very slow speed, so it was okay, but yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it it's on, but.
No, but bring it closer and.
Oh yeah, look at that. Okay, we turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement.
Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets.
What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay,
Work together.
yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is there
What
a
do
way
we...
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo, and prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh,
Is that a magnet?
this? No.
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just for...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks, because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you.
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got,
2 electromagnets, 1, 2.
and those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
that's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready, let's do it.
Okay.
My goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets!
Woo!
You wanna go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Science Max! Stable structures are what we're building on this episode. Bridges, cups, pencils, blocks, boxes. They're all being built up and falling down. Plus, how stable can you make a structure using fruit as the base? Stay tuned to find out on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Get your hard hats out because today we're gonna be building things. Like I always say, what's the point of science if you can't use it to build cool stuff? And today's episode is called Stable Structures. Now, stables are the buildings where horses sleep. So, stable structures means... I think I have the wrong kind of stable. Today, we are going to be building a gumdrop dome. And gumdrops are already kind of dome-shaped, but they don't hold a lot of weight. Yeah, can't hold much weight. But you can make it hold a lot of weight if you build a geodesic dome. A geodesic dome means a round shape made out of straight lines, and that's what I've made here. All I used is gumdrops and toothpicks. It's very easy to make, and I'll show you how to do it. First, you need to start with a pentagon, a 5-sided figure. 1, 2, 3, 4, 5. And then stick them all together, obviously, with toothpicks. Then what you want to do is you want to start making triangles. So you stick a toothpick in here and a toothpick in here, and then you put a gumdrop at the top of this triangle, just like this. And then you make another triangle here, and here, and here, and it becomes a whole bunch of triangles, you see? Easy to make as long as you start with a pentagon on the bottom. Now, once you've built one, I suggest you build 2 more, because then you will have a stable base and you can see just how much weight these hold. Yeah. You wanna max it out? Oh, okay. Let's max it out. Oh, a little collapsing, but still not bad for gumdrops, right? So there you go, the geodesic dome. That's what you research if you want to learn how to build one of these for yourself. But now, let's max this out even more. Okay, now I just need an expert to help me out. Do you like my new interface? It's good, right? Watch this. Oh, wait a minute. That's not, okay. Wait, no, that's not the right gesture for that. It's all gesture-based, so I gotta, this? Nope. This? Nope. That? Ooh, okay. Expert. I want experts. Oh, okay. It's voice activated. Great. Oh, Sarah from Mad Science. She'd be perfect for this. Good. Close. I could leave it running. Sarah?
Hey, Phil. Back here.
Hey, Sarah. Sarah from Mad Science. Great to see you.
Thank you. Great to be here. I like your lab coat. It's a really nice color.
Wait a minute. It's supposed to be yellow. It must have changed to orange in the portal. That's okay because this is not the first time that's happened, so I've installed a little secret thing on the app that allowed me to get a new one from storage.
Oh,
Watch
perfect.
this. Huh. Didn't work. Oh well, I'll get another one later. All right. Anyway, we are going to max out the geodesic dome.
Amazing. That's so cool.
Yeah, so we just want to make it bigger. So how do we do that?
Okay, well, there's a couple ways we could do that. We could add a few more points of connection, change the shape of it, make it a little more complex so it's a little bit bigger. Or we can use the design right now and use different materials to make it bigger.
Ah, okay. Well, you know what? I think we should do both of those things.
Okay.
I think we should make it more complex and bigger, but why don't we start with bigger?
Okay.
But we'll use the simple design right here, and we'll just get like long wooden poles instead of toothpicks.
Perfect, yeah. And then, what will we use for the gumdrop?
I guess we can't get big gumdrops, huh?
No, I don't think so.
What about oranges? Huh?
Yeah, oranges could work.
Maybe, yeah, because you could stick the poles in and then the oranges would be, okay.
Yeah,
We'll go to the Science Max Fruit Market and we'll get some oranges.
Perfect.
And I'll get a yellow lab coat. I don't know why that didn't work. Is this a maxed out number of oranges?
I think so.
Or is it just a mediumed out number? We don't really need many more oranges than this.
No.
So, there we go. So we got our oranges. Those are going to be our gumdrops, and
These wooden dowels will be our toothpicks.
we just have to start with a pentagon, right?
Yes.
5 sides. So why don't we just lay that out and see what it looks like here.
We start building this dome the same as the gumdrop dome.
So, like this.
We stick the dowels into the oranges to make our 5-sided pentagon.
Good, like that.
And then we go up from there by making a few triangles and sticking the oranges on the tops.
Oh.
But because the oranges are heavy, the triangles are pretty wobbly. That is, until we get them all connected with cross pieces.
Yeah.
After that, it seems to hold up pretty well.
Okay, let's see if it holds it up. Whoa! That's exciting. That is very exciting. Let's do the same thing. So you make a triangle here, I'll make a triangle there, and then we'll connect them.
Sounds good.
2 layers, orange dome. I'm pretty excited about this. This is nice.
Yeah.
I'm surprised that the oranges actually hold it together because oranges aren't really that strong.
No, exactly. But the structure itself is really strong based on the design of it.
Yeah, because it's all about the shapes, right?
Exactly. And we're using lots of triangles today, which are one of the strongest shapes on Earth.
Ooh, strong. Well, then making something out of a lot of triangles makes it really strong.
Exactly.
Yeah, okay, so let's make that top layer of things. We only need 1 more orange.
Yeah.
This will be the one, top layer.
Right in the middle.
1 orange on top with 5 dowels from each point and...
Yeah! Orange juice, high five.
In fact, it worked so well, there's only one thing left to do.
Is there a way that we can maybe max it out even more?
Watermelon? Watermelon. We could get the round watermelons. You ever seen those? They're like the size of a bowling ball or smaller, a little bit smaller.
That's perfect, and they're nice and full inside, so they should be able to hold the posts into place.
Okay, we'll try it one more time with watermelon. Inside dome, high five. Yeah! You may have heard of cup stacking, and if not, you're missing out because not only is it fun, but it's something that kids are the world record holders at. And it's all about, you guessed it, stacking cups. Now, I have learned the pattern, but I'm not super fast at it. The world record is actually 4 seconds, and this is what that looks like. But you can't use camera tricks to help you. You have to practice to get faster. Now, you don't need to use official sport stacking cups, but if you don't know your science, some things will work against you. First of all, these cups have holes in the bottom, which makes them not very good as, cups. Why do they have holes in the bottom? Because of science. You see, when you pull the cups apart, there is air that needs to get inside this cup. If you don't have a hole, like these ones, the air makes them stick together because there's nowhere for the air to get in except for underneath, and they will stick. Once again, let's compare. Also, you want the cups to have some weight because if they have some weight, they'll fall out of each other easily. If they don't have any weight, like, say, these styrofoam cups, it becomes very difficult. And cup stacking with trash cans. Okay, here we go. Even though these trash cans were heavy, they didn't have holes in the bottom, which means they stuck together. A lot. So why didn't I drill holes in the bottom of these trash cans? Okay, and then, well, I needed them in episode 6 to make 11 barrels of slime. Okay. 2. No. But I eventually did it. And time. Okay, there you go. The world record in trash can stacking. I know it doesn't seem very fast, but first of all, that was hard. And second of all, I am the only one to do it. So therefore, I hold the record. Sarah and I have already made a great dome out of oranges. Now we're maxing it out even more, but this time using... Watermelons! But not the giant watermelons, the perfect spherical watermelons. They'll have to do pretty good to be better than the oranges.
Definitely.
All right, so we just do it the same way?
Same way.
All right.
Let's do it.
I'm sure I'm not telling you something you don't know when I say watermelons aren't great for building structures with.
This is super wobbly.
But the fact that we can make a structure using watermelons just proves how amazingly strong a geodesic dome really is.
Have we done it?
Yeah.
We've done it! Yeah, watermelon dome!
All right, we've got our gumdrop dome.
We've got our orange dome.
And we've got our
watermelon dome. These are awesome maxed out domes. What do we want to do to max it out even further?
I think the watermelons were a little too heavy. Maybe we should go back to something lighter.
So we can make it out of gumdrops, which will be like more complex.
Exactly.
And we won't get orange juice raining on our heads all day, which is what happens with this one.
Max Historica. This is Leonardo da Vinci.
Ciao.
One of the greatest inventors to ever live. And this is a pile of wood. One of the greatest piles of wood to ever be piled. Now, Leonardo is going to construct a bridge out of this wood. This is Leonardo's hammer. One of the worst hammers in the history of hammers. Now Leonardo must construct his bridge using no tools at all. No, that hasn't been invented yet. How will Leonardo construct a bridge using no tools at all? Well, he is one of the greatest scientific minds. One of the greatest scientific minds in history. Oh-ho! Each piece of wood is supported by another. And that's what's known as Leonardo da Vinci's self-supporting bridge. Leonardo's done it! But there is a flaw in the bridge. It's very strong when you apply downward force, but not so strong when you push on it sideways. Fortunately, Leonardo can devote his great mind to figuring out how to clean up his workshop. Haha! Join me, one of the greatest narrators in the history of narration, next time on more Max Historica. Let's recap. Sarah and I have maxed out our simple geodesic dome, but now it's time to make it even more maxed out. We need to increase how complex our structure is.
So right over here, we actually have a dome that's just made out of triangles.
Ooh, look it. It's nothing but there's triangle there, there's a triangle there, triangle there, triangle. So all triangles.
All triangles. And see how much bigger it is even compared to our first one?
Yeah.
And that's just by adding more points. Over here, we have one that uses pentagons and triangles.
Ooh, let me see. Okay, so we got, oh, there's a pentagon there.
Yep.
There's a pentagon there. And then we got triangles here.
Yep.
Can we go bigger than this? Because this is good, but this is not maxed out enough.
Sarah had the idea of lengthening the poles.
Shish kebab skewers, I love those. I use those all the time in my science experiments.
And making a bunch of pieces that fit together.
So we just make a whole bunch more of these.
Yep.
And then we'll make some sort of big dome.
This is awesome! So we maxed it out, and it worked great. But gumdrops started to become a little hard to work with.
Every time I do one attachment, another one comes apart. So I had to get inside to hold it up with my head.
I think I've got an idea.
Oh, yeah?
Be right back. Yeah.
Okay, but should I get out or should I? It's okay, I can stay in. I can just keep fixing while it's collapsing a bit, but it's okay. Wait, this is inside. No, this is outside. Wait, hold on. Help, Sarah?
Hey, oh, my.
It kind of collapsed a little bit. Gumdrops, they just don't have the strength.
Exactly. I was thinking we could use something a little more sturdy, maybe like some cardboard.
Oh, yeah, and it doesn't move at all. We can totally make this, we'll max this out. I'll just put this over here. Okay, fair enough. Okay. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books.
The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is.
Right now, it's pretty wide and it's not that tall, so the center of mass might be around here.
But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider.
The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, whoa, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And, ha-ha, a single stack of boxes. Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! Science! Science!
is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube. If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks. Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go? Ooh, look it. Sarah and I have maxed out a geodesic dome out of gumdrops, oranges, watermelons, and more gumdrops. But now we're making one using glue and cardboard circles. Are those the same distance? After a bunch of time assembling and gluing, we have a giant maxed out dome. Okay, there, are we done?
I think so.
We're done!
Yeah!
Yeah! Max out dome. How many points do we have?
So many.
Do you think we can lift it?
I think
I think
so,
that's the
yeah.
top. Try it.
See.
Okay, whoa. Whoa! Wait, we can spin it! It was really light and also really strong. Strong enough to hold upside down. As a fruit bowl, it'd be pretty good. This is so strong. I'm surprised at how strong this structure is. There you go, Science Max, experiments at large, geodesic dome. And now it's sort of a geodesic disco ball. I like it. Whoa, 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 okay, careful. Careful, careful. All right, putting it down, putting it down. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two... Oh,
are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel. See, they don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. Whee! But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put two around a pencil and then four more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Job Master Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on that, step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Oh, look at that. You could totally, oh, wait a minute. Totally. It doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And. Ha! Am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh, yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, haha, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science!
Turns out, trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Let's get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong.
and I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got two more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science.
So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear, no, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get into the camera.